Good day everyone, my name is Colin Mann, and today I would like to discuss with you where I see the technology in commercial aviation aircraft navigation is going and how I see the basic training changing to support this shift. To give you a better understanding of where we're going, I first need to take a few minutes to explain to you where we've been and where we are now. As most everyone knows, the first powered flight was carried out in 1903 by Wilbur Ernova Wright. The Wright Flyer flew 120 feet in 12 seconds at approximately 6.8 miles per hour. Of course, at this time flights were so short, navigation wasn't really yet much of a concern. However, to calculate airspeed, a critical component of navigation, the Wright brothers used a mechanical anemometer and a stopwatch. These devices would continue to be developed through the early days of flight to employ a timing device and a cockpit indicator, providing the pilots with calculated indicated airspeed. Skip ahead just 11 years to 1914. This was a historic moment in aviation. It marked the beginning of the first passenger air service. This was a 21-mile flight that could carry one passenger across Tampa Bay, Florida in just 23 minutes. In these early days, flights were restricted to good visibility and weather. To navigate distances, pilots would plot a course on a chart based on landmarks along the road, such as roads, railroads, rivers, and lakes, etc. This navigation was known as pilotage. By the mid-1920s, the U.S. military and the U.S. Post Office deployed a line of rotating beacons spread across the country at a distance of about 80 miles apart. This system enabled pilots to fly the route at night, and mail could now be delivered across the country in as little as 29 hours. This was 2 days faster than by rail. Then, just 5 years later, in 1919, the first successful transatlantic flight was flown by British aviators John Alcock and Arthur Whitten Brown, using only a compass, sextant, and charts as their means of navigation. For those who don't know, a sextant is an instrument that was used to measure the angular distance between an astronomical object and the horizon. Navigators could then plot their position on a navigational chart. The compass became one of the first flight instruments used by early navigators. However, these liquid-filled compasses were not perfect by any means. Steep turns, engine vibrations, and pitch changes caused inaccurate heading information, and magnetic and field interference from metal parts of the aircraft would corrupt the compass without heading correction. Early pilots recognized that the fastest and most efficient route was to fly in a straight line rather than between 2 points, rather than following winding rivers and roads, and so began the next stage in evolution of navigation known as dead reckoning. This is a process used to determine distance traveled by multiplying the time traveled by the aircraft's indicated airspeed. This also required a great deal of guesswork to compensate for aircraft drift depending on wind direction. Charles Lindbergh used dead reckoning for the first solo non-stop transatlantic flight from New York to Paris on May 21st, 1927. This was a 33.5-hour flight. As aviation evolved, it became abundantly clear there were significant limitations with air travel. Things like severe weather, clouds, and course drift made navigation extremely difficult at best. So if aviation were to expand, more accurate navigational aids needed to be developed in order to keep pace with the increasing aircraft performance. From 1928 to 31, significant advancements were made in developing radio frequency direction finders as a means in navigation of aircraft. By broadcasting and receiving radio frequencies, a course or bearing to a station could be determined with the invention of timekeeping technologies such as the crystal oscillator. The systems were able to fix their position with a good degree of accuracy. By World War II, a web of air navigation radio stations and beacons began to cover most of the globe. Here you see a radio compass indicator and an RCA range receiver. This is a typical radio range receiver used in late 1930s on private aircraft. Other fields of radio research led to the development of radar, which could detect objects by bouncing radio waves off the object. And in 1935, the first radar system for detecting aircraft was deployed in Great Britain. This is a memorial dedicated to Robert Watson and Arnold Wilkins, who were accredited for developing this technology during the war and saving the RAF from defeat. Later advancements in radar led to its installation onto aircraft, allowing detection of weather patterns, terrain, other aircraft, and providing aircraft traffic controllers with a means to control and guide aircraft into airports. This system is still a primary means of detection used today. The true success in commercial aviation came in 1936 with the introduction of the DC-3. The DC-3 had such improved range, speed, and reliability, it was able to provide transcontinental passenger service across the U.S. This would not have been possible if not for the advancements in radio wave guidance technology. The use of radio frequencies proved to be the solution to bringing accuracy and reliability to aircraft navigation and remains to be the base of all navigational position and direction finding today. There have been vast improvements in antennas, transmitters, receivers, and, with the onset of computers, carrying out rapid and highly complex calculations based on changes in wavelength propagation has allowed us to develop far more sophisticated and accurate means of determining where we are and where we're going, as well as providing a reliable system for detecting and avoiding, as we mentioned, severe weather patterns, terrain, other aircraft, and as things have advanced, ATC has been able to provide control over aircraft in highly congested airspaces. Here you'll see some examples of position computation ground-based navigational aids. Things such as non-directional beacon, VORF, omnidirectional, or VHF, sorry, VOR, but VHF omnidirectional rangefinder, ADF, which stands for automatic direction finding, DME, distance measuring equipment, and of course for guiding aircraft into landing, which is an instrument landing system along with glide slope and radar guidance. These conventional means, although are effective, have now become less effective due to the increase in performance and primarily due to the significant increase in air traffic. The common issue with the conventional navigation are as follows. It requires large protection areas and large separation criteria to cope with its limited accuracy on position. Inability to provide direct course routing, operates by line of sight, is giving limitations in accuracy over oceans and mountainous regions. This is all leading to traffic saturation, which in turn leads to increased fuel burn and more pollutants in the environment. So, to meet these new demands, development and implementation of a highly sophisticated and highly accurate global navigation system known as GNS was established. The U.S. developed a global navigation satellite system of their own, known as Global Positioning System, or more commonly known as GPS. This system was first launched in 1978 and reaching its full operational capabilities in 1995. The system has rapidly developed and expanded to what is now a total of 31 active satellites orbiting at approximately 20,000 kilometers above the Earth and reaching speeds of up to 11,000 kilometers per hour, with each satellite completing 2 orbits of the Earth each day. The GPS system is based on the broadcasting radio frequencies that include time and known position of each satellite. A GPS receiver monitors multiple satellites and solves equations to triangulate the precise position of the receiver. At a minimum, 4 satellites must be in view of the receiver for it to compute its known position. As you see here, an aircraft traveling along with a range of 4 air satellites, computing its heading as well as its position. Other global navigation satellite systems were established. The Russians developed one, as well as the Chinese. The European Union have one, as well as India, and Japan is still in development. As air traffic expanded globally, so did the need to standardize conventional flight. To provide this standardization, the establishment of the International Civil Aviation Organization, or as ICAO, was formed in 1947 as a specialized agency for the United Nations. This organization continues today to guide the principles and techniques of international air navigation, as well as fosters the planning and development of international air transportation to ensure safe and orderly growth. In 2003, with the onset of global navigation systems, ICAO began to standardize performance-based navigation, known as PBN, in the form of a manual. This manual is used today to specify the navigational performance requirements for aircraft to be defined in terms of accuracy, integrity, availability, continuity, and functionality required for a specific airspace. In 2000, GPS receivers had an accuracy of about 5 to 20 meters. This system alone could not meet the PBN requirements, so the US began to resolve this issue by developing what is known as Wide Area Augmentation System, or WAAS. WAAS was able to correct GPS signal errors caused by ionospheric disturbances, as well as timing and satellite orbit errors. The system uses a network of precisely located ground reference stations that monitor and process GPS information and send the information to the WAAS master stations. The WAAS master stations then develop a correction message and send it to a WAAS-enabled GPS receiver. By integrating the WAAS, GPS signal accuracy has improved to approximately 1.5 to 2 meters between the horizontal and vertical planes. In July 10, 2003, WAAS was activated, allowing pilots for the first time to rely on the GPS system as a primary means of navigation. So you see here, receiving the GPS satellite information and then a corrected message in order to give it greater accuracy. The establishment of WAAS and further development of the baseline satellite constellation has led to the next phase and future of aircraft navigation. Automatic Dependent Surveillance Broadcast, known as ADS-B, is the next generation of surveillance technology in which an aircraft can automatically determine its four-dimensional position, including speed, via satellite navigation. This enables it to be tracked to a very high degree of accuracy. The information can be received by air traffic control stations to guide aircraft without the need for radar interrogation. It can also be received by other aircraft to provide situational awareness and allow self-separation. How does it work? ADS-B equipped airplane has a special transponder that works with the GPS and ground stations. These have the ability to automatically transmit and interpret very accurate data to other ADS-B equipped aircraft and air traffic controllers. ADS-B is superior to conventional navigation in many ways. Just to name a few, we have reduced aircraft separations, trajectory-based operations providing gently ascending and descending gradient with no step-down or holding patterns needed, improved air traffic control, better air traffic flow, reduced fuel burn through more efficient flight profiles, lower EMF than radar, which equates to being less harmful to people, and the list goes on. At this point in time, however, technology is not yet fully capable at all altitudes globally, due to the lack of ground infrastructure in many countries. However, as this system continues to demonstrate its cost benefits and increased safety capabilities, it will soon become adapted globally, and due to its superiority, it will soon replace conventional navigation as the primary source for all aspects of aircraft navigation in the future. As we move towards a more sustainable and environmentally friendly propulsion systems, the world will become saturated with a wide assortment of flying vehicles. This increase will dramatically impact air traffic. This new, evolving, and highly accurate technology will meet those demands and will eventually lead to fully or very nearly fully autonomous air traffic control and aircraft flight. As the technologies evolve and rapidly advance, the knowledge to support these new technologies will be vital for operating and maintaining these systems. As we move into this new future, student training will need to adjust to this new technology. Basic training for aircraft maintenance engineers, M category as well as E category, will need to be provided with increased understanding and developments in data link communications, computer programming, computer function, software utilization, interrogating of aircraft computers, and fault isolation of these new systems, just to name a few. At some point, due to the advancements in aircraft systems and navigation, I see the industry pushing to tie these two categories together. As systems for modern aircraft have become and will continue to become more and more computer integrated. Even now, companies maintaining these machines find themselves constrained by the divide between these categories, and soon will demand a more dynamic and versatile technician to provide companies with an increased manpower utilization in order to maintain profitability. The possibilities for the future are limited only by our imagination. Thank you all for listening, and enjoy your future.